Hello and welcome to Tiger Astronomy, the home of professionally developed and supported software, instruments and automation systems for astronomers. My name is Tim Long and I'm here today to talk to you about the Reactive Communications library for ASCOM, which is a library we produced in response to problems we had with some of our own drivers where they basically broke down under operation from multi-threaded client applications. And what would happen is um, once the client was sending different commands on different threads, the commands and responses would get all jumbled up, and we spent a great deal of time trying to thread proof our drivers and kept running into all sorts of problems. And we uncovered quite a tricky problem to deal with, which has to do with reentrancy, which is a situation where thread locking primitives don't work, because if the code happens to be running in a single threaded apartment, then everything is running in just one thread. So locking the thread is meaningless, because if another piece of code is called reentrantly, well, it's on the same thread, so it's not prevented from running. So um, there are various ways to approach a solution to this problem, but the way we have approached it is to step back from the problem and try to think about a general purpose, high level solution, a good, well factored object oriented design that not only solves the problems but is easily reusable across a wide range of drivers. And since we thought it was a useful solution, we decided to make it available to other people to use as well. So, what is the Reactive Communications Library for ASCOM? Well, as the web page says on the screen, it is a reactive style transactional device communications library for ASCOM drivers with guaranteed sequencing and thread safety. Well, that's quite a mouthful, so let's break that apart a bit and see what that really means. Well, reactive style. The word reactive relates to the fact that we've built our solution on the reactive extensions for .NET, which is the reactive extensions are really a different way of looking at data streams and how you manipulate and respond to data as it arrives on your system. It's kind of a bit analogous to an IEnumerable of something, and then you can have an iterator which iterates over the data. Well, that's really looking at the data as a pull collection. You ask for the next piece of data and you wait for it to be ready. Whereas the reactive extension kind of goes through the mirror and looks at the data from the other side and treats data as a push collection. So what you do in reactive land is you make queries for your data which are deferred. They don't execute straight away. Rather like link queries, nothing happens until you ask for the results. But in reactive, you put your queries in place and wire up all the code, and then nothing happens until the data arrives. And when the data arrives, the right piece of code is automatically run at exactly the right moment. It's kind of a different way of thinking about things, but it does work rather well for writing more asynchronous code, and the queries that you can produce are composable, so you can make building blocks and string them all together. So our solution's built on top of that. It's a transactional system because the basic unit of transfer is the transaction. We have a class called a device transaction, and when a user writes a driver based on this system, they will basically produce custom transactions tailored for their application, and we'll go into that in some more detail perhaps in another video. But for now, the last part of the puzzle is that you get guaranteed sequencing and thread safety, which is really the big problem that we were trying to solve for our own drivers. We wanted our drivers to be thread proof so that it doesn't matter how many threads the client app uses, and we're guaranteed that our commands and responses are all going to line up no matter what the client application does. So in this first video, in our tutorial series for the Reactive Communications library, I'm going to talk about the basic principles, the minimum requirements that you have to have in place for using the library. So we'll write a very simple console application right from file new project, and we'll go through all the steps you need to take to get set up and be ready to run. And I think you'll agree by the end of the tutorial that it's actually really quite straightforward and easy to do. So without further ado, file new project. Okay, file new project, and we'll be creating a console app targeting .NET Framework version 4.7.2. We'll call this Reactive Comms Demo, and OK. Okay, so the first thing to do is to bring in the NuGet package for the Reactive Comms library. So if we just right-click on References and click Manage NuGet Packages, and make sure you don't have Include Pre-Release selected here. Click on the Browse tab and go ahead and put ASCOM in the search box. And after a little while, we should come back with some results. And here we are, ta.ascom.reactive communications current version as of the 28th of August 2018 is version 1.1.0. So install that. Now, all the stuff you can see scrolling in the output window these are not dependencies of the Reactive Comms library. So what's happening here is, because it's the first NuGet operation in a new project, the Visual Studio is bringing in all the runtime packages. So don't worry, you're not taking dependencies on all these things. Okay, we need to accept the license agreement for Reactive Comms, the Reactive extensions for .NET, and that should be us done. And here we have okay, TA ASCOM Reactive Communications, perfect. Done with NuGet for now. So let's get started. Okay, to use Reactive Comms, there are two things you absolutely have to have, and a third thing that you probably will want to have. So the first of those things is a communications channel. This represents the device you're communicating with, and it abstracts away the details of the hardware. So note, as we're coding, we never mention a serial port as such, but we will mention a communications channel. So in order to create a communications channel, you need a connection string. And this is a concept we borrowed from SQL Server databases, where you specify the database and all the options just in a string. And the nice thing about doing it that way is that you can take your string and just store it directly in your driver settings. We find that a rather convenient way of doing things. So the connection string will be COM1, and then we can put serial parameters here, and I'm just going to put 9600 bits per second, or BALD. And then in order to create the communications channel, we can't just new up a serial channel, because that would be tying us to serial. So one of the concepts behind Reactive Comms is that you're not tied to a particular type of channel. The user could change between different channels just by changing the connection string in the settings. So we have to use a factory class to create our channel. So we need to first new up the factory class, and this will highlight that we don't currently yet have the namespaces pulled in, so I'm using Control Dot to let Visual Studio look for the namespace, and it's recommending second item here, TA ASCOM Reactive Communications. Okay, so there's our channel factory, and now we can create our channel. So channel equals factory dot from connection string, pass in the connection string. Okay, and then at some point down here we will open the channel. Now this is something you would normally do in your drivers connected property. So okay, so that's the first thing we need, a communications channel. The next concept is something called the transaction observer, and here we start to get into a little bit of terminology that relates to the reactive extensions. In reactive land, there are sequences of data which are called observables of T. So if you had a sequence of string, that would be observable of string, I observable of string, and then you have observers, which are things that subscribe to those sequences and observe each piece of data as it comes along and perform some action on it. Now, we've provided a class called the transaction observer, which is really the core class of the reactive comms library. The transaction observer performs all the orchestration, thread synchronization, and sequencing, tying up commands with responses. So it's really a critical class. So we'll just new that up. We'll call it observer equals new transaction observer, and the transaction observer needs to know which channel we're going to use, so we pass in the channel thus. And the transaction observer is an observer, an I observer of device transaction, and so it requires a sequence of device transactions to process. Now, I said you needed two things and possibly a third thing. Well, if you were experienced with reactive extensions, you might choose to finish at this point and make your own arrangements for creating the sequence of transactions. However, we think most users, and in fact we do at Tiger Astronomy, use a third class, which is a helper class, which is called a transaction processor, which gives us a simple interface for submitting transactions, and it turns those into a sequence, an observable sequence of transactions, which can then be fed to the transaction observer. So our processor is a new reactive transaction processor, and that doesn't take any arguments. And then we need to subscribe the observer to the sequence that's produced by the processor. So we do that by calling processor dot subscribe transaction observer, and we pass in our observer. Okay, and that is the reactive comms library completely set up, ready for use. All we need to do now is start submitting transactions. Okay, so for our first transaction, I'm going to use a terminated string transaction. Now, there are different types of transactions. There are a few basic, really example transaction types built into the library, but as a driver developer, you will certainly want to create your own custom transactions which are tailored to your specific application, and we will cover creating transactions in a separate video. But for now, I'm going to use a string terminated transaction. And that is a type of transaction that will look for some starting character And once it's received that, it will buffer up all the following characters until it finds some terminating character, and then that will become the result of the transaction. So as you can see, we've got a red squiggly, which means we need to pull in another namespace. So control dot Visual Studio suggests Visual Studio doesn't suggest anything because I've used the wrong name. It's terminated string transaction, not string terminated. Terminated string transaction. Control dot, and here we go. This bottom one here. Good. Now, the minimum thing we need to give to this transaction is the command that needs to be sent to the device. So these transactions are, their defaults are to work with MEAD style protocols, because that's quite a common thing used in the community. And so we might, if we were talking to a telescope, use something like, we might want to get the right ascension. So we might say :gr, which is get right ascension, and hash, and that's standard MEAD talk for commands. Always start with a colon and end with a hash, and the responses usually follow that format as well. So there are some optional parameters to this method. As you can see in the IntelliSense here, you can specify a terminator character and an initiator character, and you can see that the defaults are colon and hash. So I'm not going to specify them for now. That's all we're going to specify. So having done that, we actually, at this point, I want to take a little aside and to talk about logging, because one of the nice things about the Rx comms library is it's laced with diagnostic output, which normally you don't see. But internally it uses nlog, so just by adding an nlog configuration file to the project, we'll be able to see the diagnostic output and indeed produce some of our own. So I'm going to add another NuGet package at this point. The package will be nlog.config. Let's just search for nlog. nlog.config. Here we go. So install that. And after a few seconds of NuGettery, we should come back to, there we go. Good, we're done. So we can close NuGet again. And in our references here, you can now see we've got a reference to nlog, and we've also got an nlog.config. So let's look at this config file. This is a bit horrendous, but this is an example. Basically with nlog you can specify targets, which is where you want the log output to go, and that can be a file to the debug channel, it can be a console window or various, it can be a database, it can be over the network to a receiver. There's a lot of flexibility there. And down here in the logging rules you specify which sources should go to which targets and various other options such as that. So I actually have a code snippet that I prepared earlier for just the right amount of logging for my purposes. So let's put that in, and you can see that we're using the colored console logger. We're naming it console, and I've produced a fairly compact layout here. There is a default layout. You don't actually have to specify a layout, but this one looks nice will look nice for the demo. And we're basically logging all sources at the minimum level of debug, where the logging levels are trace, debug, info, warning, and error. So we want to ignore trace, but we want everything that's a debug or above, and we're going to write that to the target named console, which is this thing here, which is our colored console. Okay, so one more thing to mention. If we look at the properties of this file, you'll see that its build action is set to content, and that means that the build process copies it to the output directory. Now that was why I didn't just create the file, I used the nlog.config package, which correctly configures the build process. Okay, so that's done. Save that and close, and then we'll just try building this code. Okay, build started. And the first build always takes forever for some reason. Okay, build succeeded, and so we'll now try running this code and see what happens. Okay, so our first run, and let's just transition to the output. You can see my, there we go. Okay, so this is the console window here. This is Visual Studio's Diagnostics window up at the top, and the console's just quit. Now the reason that happens, this is an old chestnut. The program's run, it's got to the end and finished, and there's nothing to stop it just running off the bottom of the program. So we need to put, let's go back to the code window. We need to put at the bottom here a console.readline, just to stop the program quitting before we're ready. And I might actually, just for cleanliness, put a console.writeline, press enter. Okay, so let's try that one more time. Okay, so here's our console window, and here we see some diagnostics output. So let's take a closer look at that and just stretch the window slightly. Okay, so the first thing that happened is our transaction observer got subscribed to the transaction processor, and it reports that the pipeline was connected to a channel with endpoint COM1 9600 none 81. These are the default serial parameters. This is 9600 bits per second we specified, and that's no parity, 8 data bits, 1 stop bit. There are also some other things you can specify there, such as handshaking, but we won't go into that for this demo. Okay, and then interestingly, our program finished, and we get press enter, and yet after that we got some other activity going on. So our serial communications channel opened, and these are the comms parameters again, and our observable diagnostic extensions class produced this is essentially logging a subscription to the serial receive channel. So it's subscription number 1 in the square brackets there. So when we go into creating transactions, you'll see more of this type of thing, and that can be very, very useful to see what's going on. Okay, so that's our first run. We have diagnostics. Now we can log our transaction. Let's just press enter a couple of times. Back to the code, and now we have our transaction, and we can log it to the diagnostics output. So log. Let's use debug level. First of all, we need to create a logger. So actually, let's do that right at the top. So var log equals log manager, and control dot to bring in the namespace using nlog, and get current class logger. And that gets you a logger that's all pre-configured for the current class. Very useful. It's just a static method. So okay, down here we can now say log.debug, and then the construct I'm using now is called a string interpolation. This is a fairly new C# feature. In case you haven't seen it, it's just a little bit like string.format, except with a more compact syntax. So we've created a transaction, and then we're going to print the transaction. So squiggly brackets and then the thing you want to print, and there we go. And if we run that again, we should see that I do wish the console would remember its size. Okay, so the debugging source was program because the class name is program, and we logged created transaction, and here's the value of the transaction. So transaction ID equals 1. Every transaction has an incrementing ID, and that's useful when you produce lots of log output. You can tie up which transaction was doing what. This was the command that the transaction was created with, that would have got sent to the, well, it will get sent when we commit the transaction. You can see that the transaction, this is the response received, and you can see it currently has no value. This is the timeout of the transaction, 10 seconds by default, and the status is created, which means the transaction hasn't yet been submitted. It's just sitting there waiting for us to do something with it. Okay, and the next thing to do then is to submit the transaction. So we submit it to the transaction processor. So processor.commit transaction, and pass in the transaction. And then at this point we could go off and do some other code while the transaction's executing, or we could return to the client if it wasn't expecting a result, and the transaction will complete in its own time. Now, the most typical situation is that you want to wait for the result and return that to the client. So if that's the case, then you can call transaction.wait for completion or timeout, and you can see there's an asynchronous version of that method as well, but we're going to use the synchronous method because we want to block. And the timeout, as you saw earlier in the diagnostic output, is encoded into the transaction and is 10 seconds by default. So if the transaction doesn't complete within 10 seconds, it will time out and fail. Okay, so having waited for the transaction, we should now be able to log it again and see whether it completed. So log.debug. String interpolation, finish transaction. Oh, and the calculator's just popped up all on its own. Finish transaction. Okay. And we will now run that again, and hopefully, well, I know this is going to fail before I start because normally you'd have your drive system connected to the serial port. I haven't got a drive system here, so I know this transaction is going to time out and fail. So anyway, that's quite interesting to see what happens in that set of circumstances. So we'll run this again. We'll transition over to the output window, and there you can see that the command has been sent. We're waiting for the 10 seconds to expire, and bang, the transaction timed out. So you can see here, this is where we logged our completed transaction. Now finished or completed doesn't necessarily mean successful, it just means that all the processing has finished. So transaction ID 1 still has no value because no response was received, and the status is now failed, and the reason for failure is that it timed out. So you can see that the transaction observer has logged a warning to tell us the transaction timed out and was marked as failed, and the transaction observer then tells us that the transaction is completed, all processing finished, and it then prints out the final state of the transaction just for good measure. Okay, so normally this would, if you had a Meade style telescope or drive system attached. This would complete, and in the result value here you'd get the right ascension value. So that hasn't happened, but this gives me an opportunity to demonstrate one of the more advanced features of the comms library, which is the use of different types of communications channel. So onto that now. Okay, so communications channels. One of the design goals of the Reactive Comms library was to make it simple to write drivers that would work equally happily with different types of channel. So we aimed to produce a driver that could work over a serial channel, but then just by the user changing a preference, switch over to an Ethernet channel or a USB channel, and not have to worry about changing any other rest of the driver code. So in order to do that, the mechanism by which we abstract the hardware is the communications channel, and there's only a single type of channel built into the library, and that's the serial channel. We may at some point provide a network channel, but we haven't had a requirement for that as of yet, so it's not something we've done. However, you can write your own custom channel implementations, and I have one which I'm going to use for this demo. In the Digital Domeworks driver, that driver has a hardware simulator included, and that simulator is conveniently implemented as a communications channel. So we can, in the driver, if you download the Digital Domeworks driver from my website, you can actually set it up, and then in the preferences you can just tick use simulator, and the driver will run using the hardware simulator as if connected to the real thing. So I'm just going to reuse that simulator now in this demo. So I need that assembly, TA Digital Domeworks hardware simulator, and that requires this shared types assembly. So I'm going to bring those in as references. And then yeah, that's worked, I think. And so the first thing we need to do is to tell the library about that channel. So it doesn't just discover it on its own, you have to register it with the channel factory. So having got the channel factory, we can register our custom driver. So note that there's a method here to clear the existing registered devices, and you would do that if, for example, you wanted to prevent someone from using the serial channel. You just call clear, and then the default channels are gone, and then you can register your own. You could re-register the serial channel if you wanted, but I'm just going to leave it there, and I'm just going to register a new channel type. And a channel requires 3 pieces of information. The first thing is a predicate that tells the factory whether a given connection string is valid and appropriate for the type of channel in question. So there are some helper utilities built into the simulator endpoint class. Now, channels and endpoints go hand in hand. So if you have a serial channel, you will have a serial endpoint. If you have a simulator channel, you will have a simulator endpoint. And the endpoint is really the runtime representation of the connection string. So the connection string gets parsed in and broken up into its various components and stored in appropriate types within the endpoint. And there are also some little helper methods in there. So the first one, we need a predicate that returns true if we have a valid simulator connection string, and we can get that from simulator endpoint, and I'm using control dot here to bring in the namespace. So TA Digital Domeworks hardware simulator, and then the method we want is connection string valid. So that's our predicate. The next piece of information we need to give it is a function which takes a string, which is a connection string, and returns an endpoint that represents that connection string. So we have a helper function for that too, and that would be simulator endpoint dot from connection string. And the final piece of information is a function which takes a simulator endpoint or a device endpoint and produces an iCommunications channel of the required type. So we need to use a lambda expression for this. So endpoint goes to new simulator communications channel, passing in the endpoint. And we seem to have been missing a close parenthesis there somewhere, so that's the end of the call. Now we have a red squiggly here. The reason for that is because the parameter needs to be a device endpoint, as you can see there, but the endpoint that's being passed in is a device endpoint, but simulator communications channel expects a simulator endpoint. So since we know this method returns a simulator endpoint, then we know this will be a simulator endpoint, so we can safely just cast it as follows. Simulator endpoint, and the red squiggly goes away. Okay, so one more thing to do here, and since we are not using a serial port anymore, we intend to use the simulator. We need to change our connection string to make that happen. So perhaps I should move this line down to here because it kind of makes more sense to have it here. Oh, what did I do? Factory equals new channel factory. That's we need to create the connection string in here. So var connection string equals, and the format of connection strings for the simulator is simulator, no surprises there, and then we can put a colon, and it expects one argument which can be either fast or real time. We're going to use real time. Now in real time mode, the simulator has realistic delays and timings. If it's set to fast mode, it does everything as fast as possible, which is really useful for unit testing, and that's how we used it in the digital Domeworks driver for development. But we're going to use the real-time mode here. Okay, so the other thing that needs to change here is because we're actually now using a digital Domeworks simulator and not a Meade telescope, we need to give it a more appropriate command, and digital Domeworks understands ginf or getinfo, and that causes it to send back a long status packet which begins with v4, comma, and then a string of numbers separated by commas, and then a new line at the end. So I think that's everything we need. Let's give it a whirl. Okay, click run. Transition to the output window. Build failed. Da, da, da. Okay. Build failed. Now what was wrong? Cannot use local variable factory before it is declared. Okay, so oh yes. Obviously I have put these two lines in the wrong order. I like to keep all the mistakes in because I think it fairly shows a more realistic development experience. So let's try this again. Okay, build succeeded. Here comes the output window, and lots of output. So this bodes well. And let's stretch the window a bit, and Okay, what do we have? Oh, we still timed out. That's interesting. Okay, now, so the reason this timed out is because, okay, let's look at the code. So we've used terminated string transaction, and you remember I said this had optional parameters that had defaults that were appropriate to Meade telescopes. Well, guess what? Digital Domeworks isn't a Meade telescope, and so we need to specify different terminators. So we're going to put the initiator. If you remember, I said that the status packet begins with V4, but we can only specify a single character here, so I'm going to specify the capital V, and then the terminator will be the new line character. Okay, so our transaction will be looking for a reply that begins with a V and ends in a new line. So one more try. Okay, this looks better. So let's stretch the console window. And okay, so we sent ginf. We committed the transaction. Then you can see that the simulator state machine trundled through its internal states while it was receiving the ginf command. So we're looking kind of through the mirror to the other end of the communications link here, the simulated device, and then some more state transitions going into executing command. The state executing command says that it's processing the ginf command. The state machine then transitions to state send status, and our program then finishes the transaction, detects that it's finished, and prints out the final state. And here in the response field, you can see is our status packet. So V4, big string of numbers separated by commas, and then a new line character, and it's actually included the new line, and so the rest of that line's down here on the next line. And the transaction state is completed, which means it was successful. So the transaction observer just reconfirms that, and then you can see the simulator state machine transitioning back to its idle state, so state receiving command. So that's a successful round trip. We sent a command, we've received a response, and the interesting thing about the way transactions work is they are able to monitor the data stream and pull out the response they are expecting. So this terminated string transaction looks for the V character and then buffers everything up until the following new line. So they could have been a load of gobbledygook followed by valid data followed by a load more gobbledygook, and the transaction would have just ignored all the rubbish and pulled out the result it was looking for. So that's something to bear in mind for when you come to develop your own transactions. Okay, one more thing to consider is that now that we've processed a transaction and had a successful response, how do we get that response and what do we do with it? So in the case of the terminated string transaction, there will be a response field, and you want to first check the transaction's been successful, really, before you try going to access any response data. So there are a few fields on the transaction that are useful for this sort of thing. So we've got transaction.successful. There's also transaction.failed, which is off the top here somewhere. Yeah, transaction.failed. If it did fail, there'll be an error message, and you can also check the state to see whether it's created, pending, or completed. There is another state which is, I believe it's called hot, which means the command has been sent but the reply hasn't yet been received. So we're going to look at successful, and we're also going to check because it's possible a transaction could be successful and not receive a reply if, for example, it didn't expect a reply. So we're going to check that there was actually a response received. So transaction, we will look at the response field property, and we want to test whether there was any response. Now, that's going to look a little bit strange. I will explain what's going on here. So if we look at response, the type of that is maybe of string. Okay, so I try hard not to return nulls or have to deal with nulls in my code because they're a endless source of errors. So when I return something that might or might not have a value, I tend to use a maybe of t, and maybe is defined as something that will never be null but may not have a value. So internally, this is implemented as a collection of t, which by definition can have 0 or 1 members. So it may be empty or it may have 1 member. And because it's a collection, you can use link operators to query the collection. So response.any returns true if there are any members in the collection. And so at this point, since we know there is a member, and by definition there can be only one, we can say we can pull out that response by accessing the response property and using the single link operator. And this acts as a useful belt and braces, because if for any reason there wasn't exactly one member in the collection, single would throw an exception. So I've never seen it happen yet, but useful belt and braces. So we've got our response, and now I will simply log that at information level. So log.info received response, and then we will print out the response. And the reason that's not giving me completion is because I forgot to put the $sign on the front of my string interpolation. There we go. Okay, so in the separate video about developing transactions, you will see we look at another property called value, which the response is generally the raw string that was received from the channel, whereas value will have some kind of interpretation placed on the raw data. So for now, since we don't really have an interpretation, I'm just using the raw response. So last run then, and we should see that we get a valid response, and okay, so here we are, same as before nearly, but program is now logging received response, and here is the response pulled out of the transaction. Okay, so this is as far as I want to go with this introductory video. I think this has shown all the concepts of the Reactive Comms library. The fact that you need a communications channel, you get that by creating a connection string. The channel factory, you need your transaction observer, you need your transaction processor, you subscribe the one to the other, you open the channel, and then away you go. You create transactions, commit them, get the results back. So hopefully you can begin to see some of the power of this technology, especially the fact that we didn't really have to change any of this code down here when we used a different type of channel. So that's it for now. Look out for other videos on creating transactions and other topics, and I hope you found that useful. My name's Tim Long from Tiger Astronomy. Thank you for watching, and goodbye.